So thank you very much, Drew, for inviting me. I'm very happy to be here, although virtually. So the idea of today's practical example is to guide you step by step through the process of using growth curve analysis to model pupil data. And to do that, I'm going to use my own data from my PhD project. So I'm going to show you how I analyzed step by step my data using growth curve analysis. So this project is, its title is Pupil Size Tracks Uncertainty in Word Meaning Access. And for you to understand where does this data come from, and also what are the research questions that I'm trying to answer, I'm going to start with a brief introduction of my research motivation. So what I study is semantic ambiguity, which occurs when a word has multiple meanings, and it's an interesting phenomena because on the one hand, it increases the communicative power of language, but at the same time, it may represent a potential challenge for human language, because each time we encounter an ambiguous word, we must decide which of the meanings is the correct. So how do we make this decision? Well, there are several factors involved in this moment of disambiguation. I'm going to focus in just a few of them. The most studied factor is the relative frequency of the meaning. So usually one of the meanings is more common, so it's easier to process. We also have the context of the sentence in which the ambiguous word appears, such that it speeds the activation due to semantic or syntactic restrictions. And finally, we also have another kind of context, that is the global context, which is the general topic of the discourse in which the ambiguous word appears. It will be the topic of the text we are reading, the topic of the conversation we are having, and it has been shown that word processing is facilitated when global context is related. So during my research, I'm going to focus in this last factor, the global context, and what I want to know is how does it affect the processing of ambiguous words. I'm going to put the pointer here. Okay, so one way to study the word processing and effects of factors in word facilitation or difficulties is to use a tool that by now you already know, that is pupillometry, which is the measure of pupil size. And in particular, there have been several studies relating pupil size to language effort, language uncertainty, difficulties, etc. I'm going to show you some of them here. For example, there has been shown a greater pupil dilation for low versus high frequency words, greater pupil dilation in the presence of noise, greater pupil dilation in the processing of second language. And also, it has been shown a greater pupil dilation in sentences with ambiguous words. In this case, it was in the context of a sentence, not an isolated word. So this was it seemed like a very useful tool to answer the questions that I had in mind. So to specify my research questions a little bit more, these are if the global contextual information reduces the neurocognitive demands, that is, facilitates the processing during word disambiguation. And I'm also interested in evaluating if this global context effect is specific to words with high ambiguity, or maybe we also find this effect in non-ambiguous words. Okay, so I didn't say that, but please stop me whenever you want. I know it may be a little bit more difficult to stop me because you have to stand up, but I really encourage you to stop me at any point of the talk. Okay, so what is the protocol that I used in this experiment? It was a pretty simple protocol. It consisted of the presentation of a text together with an image, which represent the global context. And it was followed by a semantic relatedness task in which the critical word of interest appeared. In this case, it is the word note. In this task, participants listen to two words, one after the other, and they have to decide as fast as they can if they are related or not. And importantly, this first word, that is the word that we are interested in evaluating the processing, can be ambiguous or non-ambiguous. And they belong to a certain category. So for example, in this case, the category is music. So an ambiguous word coming from the music category would be note, and a non-ambiguous word coming from the music category would be guitar. And also, we have two conditions regarding the context, because this context previous to the semantic relatedness task can be a text that is related to that category. In this case, it would be a music-related text, and we will call that the match condition, or it can be a text that is not related to the category, to any of the meanings of the word. In that case, it would be an unmatched context. So the unmatched context would act as a control situation in which we expect that it won't bias the interpretation of the word note, whereas we expect that the matched context will bias the interpretation of the word note, and thus the relationship between the word note and the word song will be faster and more accurate than when this context is not related. And two important things about this protocol is that since we are recording pupillometry simultaneously, we have a baseline that I think that you already talked about that. You have a baseline in which the cross appears on screen and just remains there, and people have to stare at it. And then during the task, the screen is exactly the same. It's a cross on the screen, and they listen to the two words. And this is important because we didn't want people to read the words because they would be moving their eyes, and we want to have the clean pupillometry data. So we want the eye to be fixed in a place. So that's why this protocol is auditory and not written. So we have 512 trials per condition, and that is basically the protocol that we have. So to sum up, we have two variables. One is word type, ambiguous and non-ambiguous, and the other variable is context. We have the matched context and the unmatched context. Are we okay? I think I won't hear you, but hope we are. Great, I heard something. Okay, so let's go now to the part that we are interested in, that is how do we analyze this with growth curve analysis? So I've been using growth curve analysis actually for a little while because I showed Drew my data, and she suggested me to analyze this with growth curve analysis. But as she said several times, it was a very nice transition coming from GLMs and mixed models in general, because as you saw, we used the same libraries. and the logic, it's very similar. So I think that maybe the interpretation part is a little bit more difficult, but how to construct them, it's very intuitive. So just to say it again, but what are growth curve analysis? They are mixed effects modeling in which we will define a functional form to describe effects that are non-linear in time. So here we have the response of the pupil evoked from a task as a function of time. And you can see that this is clearly not linear, right? So we will define a functional form that will describe this. We have to find a functional form that describes this. And the mixed effects part is because basically we are adding the random effects. So that's why the mixed word is here, because we will have, apart from the fixed effects, that will be our variables, and the variables that we assume that are equal to each of the observations, we'll also have variance that comes from the stimuli we're using, the participants. So these random effects will account for that variability. So what happens is that when we see the pupil curve evoked by a task, higher order polynomials are usually a good choice to use as a functional form. Due to the shape of that curve, we usually can fit pretty good the curve that derives from a task. So what are higher order polynomials? These things that I'm showing you here, we have coefficients and we have the different, the linear, the quadratic, in this case up to cubic. And we will use this kind of structures to model this. What are the advantages? First of all, we are treating time as a continuous variable instead of using intervals. This is good because we usually miss a lot of information if we just take the mean of a whole window. And sometimes you may also not know which window is the appropriate to use. So that is an advantage of this kind of analysis. And also we are able to model the nested structure of the data with this mixed effects modeling. So yeah, as Ruth also told you, I highly recommend reading Meerman's book, and he also has a blog in which he has a few more things. So what are the steps into using growth curve analysis? The first thing that we have to do is to determine the area of interest. We have our whole recording, and we don't want to model all of the time series. So we have to determine the area of interest. Then we have to choose the functional form. We said that we had to choose a functional form in order to model a nonlinear effects in time. So we have to choose it. We don't know which one to use in the first place. Then we have to determine the random effect structure, which is the mixed part of the model. And finally, we have to test our experiment variables. So usually this is the part that we are most interested in, but we have to do several things before actually testing if our variable has any effect or not. So these steps, I'm going to show you a little bit of code here, and most of that code I took it from this paper, this Drew's paper that has the scripts open. So I will not upload any script, but you can find those same or very similar chunks of code in this paper. Okay, so let's start by loading the packages. I put this here just to show you that if you already use mixed models, probably you already know these packages because they are the ones that you usually use, ggplot, LME, LMER test. We are not doing anything much. We are not using any strange package. And then we will load our data. And this is how my data looks like. I wanted to show you which are the columns that I have. I have the different IDs. I have the categories. I have if the variable of interest context in which I'll have matched and unmatched levels. I have the word type in which I will have ambiguous and non-ambiguous levels. I have the word that these are the words that will be ambiguous or non-ambiguous. In this case, flamenco is ambiguous. Then we will have the time beans, that is the time. And then I'll have the pupil trace, that is the value of pupil size. So, as I told you, the first thing that we have to do is I want to hide this. I'll put it here. No. Well. Okay. So the first thing that we have to do is to select the area of interest. And a good thing that we can do is to plot the pupil size without plotting the different conditions separately, right? So this is what we have here. We have first the 2 seconds of baseline. This is when the participants listen the first word, that is the word that we are interested in. And then the second vertical line is the one that corresponds to the second word that they listen to. But as I told you, we are not interested in modeling this whole trial mainly because we are interested in just evaluating the effect of the context in this first word. So we are interested in this little part. And also because growth curve analysis wouldn't be able to model this whole complex shape. So the idea here is to select a window that is able to capture the whole response, but also is able to model it with a polynomial basis. So as I told you, we have the baseline here that specifically it is the 500 milliseconds previous to the presentation of the word. And then if we zoom in, this is the response that we are interested in. And we'll see that we have a small delay in the response. So a good area of interest would start at this point where the response starts, that it's approximately 500 milliseconds after prime onset. And the end of the area of interest is a little bit more easy because it's the beginning of the second stimuli. I'm no longer interested in what happens after that. So basically, we selected the time window that I'm showing you here that really captures the whole response. And it's just a small part of the whole trial. So this is just how you implement it in code. You filter your data just to keep time beans in the selected zone. And we are done with the area of interest. So now let's move on to the choosing polynomial part. We have to choose a functional form. And in order to do that, we will start by creating those polynomials. So to create those polynomials, we are going to use the poly function that automatically gives us the orthogonal polynomials. Remember that we use the orthogonal polynomials because the orthogonal part removes the correlation between one and other. And here we specify the number of degrees that we want to create. And this is usually a good number, so we don't want much more. We don't want a super complex model, so we are not going to put 10 degrees here. And usually this is you can check how many inflection your curve has to estimate more or less how many polynomials would you need. But first, we're going to start with 4. So what this function is creating is a linear time, a quadratic time, a cubic time, and a quartic time. But actually, it's not just time because it's the orthogonal time. So this would be a little bit more strange than just this. Then what we will do is just create a data frame with this. So we create columns. Each one of these is a different column, and we will stick this to our previous data frame that we had here. So we want now to have also the polynomials. That is basically what we have here. So this is what we had previously, and now we are adding 4 columns. Each one of them corresponds to this, this, and this, but orthogonalized. So up to here, we have created the polynomials. This doesn't mean that we are going to use them. We are just creating polynomials to test. Now we have to test them. Do they improve fit? Is it worthy for me to add this polynomial to the model? So what we are going to do to test these polynomials is to take a very similar approach to the one that Drew already told you. That is constructing models that one by one add each of the polynomials. And what we will do is to compare the model that does not include the polynomial with the one that includes the polynomial. So for example, here we have the pupil trace as a function of the intercept. So this does not include any polynomials. And we compare this model with the model that includes the poly1 term. We will do an ANOVA, and we will see if including the poly1 term improves fit. And what we see is that it does. So we do the same with all of the polynomials. So see that here I'm also including poly1, but I'm adding poly2. So I'm comparing this model with this one, and I also see that it improves fit. And I do this with poly3 and poly4, and what I found out is that the linear, quadratic, and cubic polynomial improved fit, but the quartic did not improve fit. So what I do is I just include up to the cubic polynomial. What you can also do is to check, to visualize if my data actually fits a cubic polynomial. And so if we plot the points are the real data, and the model prediction is on black, and we see that it does pretty well. We have already selected our polynomials. It will be up to the quartic polynomial. So up to here, we don't have any conditions yet. Is everything okay up to here? I don't want to.
Yes. Yes.
Okay, so we'll move on to the part of determining the structure of the random effects. So remember that on these models, we have to add a random effect structure. And what we will aim is for the maximal structure of random effects, which is basically this one. So what do we have here? We have that all of these things vary between the IDs, between each of the participants, and all of these things also can vary between each of the words. And what are all of these things? Well, this is the intercept. So I'm saying each participant can have a different intercept. This is the linear term. So I say each of the participants can have a different linear term, that is, can have a different slope. And the same for poly 2 and poly 3 and for the words. So this would be the maximal structure. And this is something important that Drew already told you, that model with complex random effects can take a long time or can also fail to converge. So this is important maybe for the last part where you start adding the experimental variables. Sometimes you see there that models don't converge. So what you usually do is to simplify the random structure. So you would start deleting this poly 3, for example, this poly 2, and so on. Okay, so how are we going to test this random effect structure? Exactly the same way that we've been doing, that is basically creating a model that adds the term and comparing it with a model that does not have a term. So this model without word is the model that we started from, is this one. What we are going to do is to add random intercept for words and see if this improves fit. We will do the same, but now adding the random slopes, and I'm not going to go through this whole procedure, but basically we'll add one by one each of these terms and see if they improve fit or not. And what we see in this case is that all models converge and they all improve fit. So basically we keep this maximal structure for our following models. Okay, so we are done with the first 3 steps. And now we have the final step, that is testing our experimental variable. So up to now, we didn't include any experimental variable. We were just doing all of the things that surround it. But what we want now is to test if there are any effects of context and of word type in this case. So this is the whole model. This is the model with all of the experimental variables and all of the interactions. But let's try to understand what each of these lines mean. So the green part is the part that you have already seen. That is the fact that pupil dilation is predicted by time and that it changes as a linear, quadratic, and cubic function. So that is the part that you have already seen. Now I added the experimental variables. What I added is the fixed effects of context, the fixed effect of word type. This would be the intercepts, the interaction between them. And then we also have the interaction between each of the experimental variables and the different polynomial terms. We'll see in a while what this means more in detail. But basically, we are saying that the changes in time are also affected by the experimental variables. And then finally, we have the random effect structure that is maximal, as we just saw. So if we plot the predictions of this model and we plot the real data as points, what we see is something like this. We have a plot for the ambiguous words. We have a plot for the non-ambiguous words. The 0 here is the moment when they listen to the ambiguous or non-ambiguous word. And this is the pupil response. And we can see that the models do a pretty well job in recreating the curves that we see in the real data, right? So how can we see if any of these factors is significant? Well, the first thing that we can do is, again, compare a model that includes the term with a model dropping that factor, and we will do likelihood radio tests. So this is a table that summarizes all of those models. So this is not a table that R just gives you, but this is a table that you construct that basically has the values of each of the models that compare this model with the model, for example, dropping this interaction. So this would be in the table, and we will have the p-values, degrees of freedom, and the chi-squares. So let's see what this means. This first 1, 2, 3, 4 3 lines correspond to the things that we tested at the beginning. We already know that the quadratic polynomial will be significant, that's why we included it, and that the cubic polynomial will be significant, that's why we included it. But then what happens with the rest of the factors? What we see is a significant improvement in the fit of the model when we include context as a fixed effect, and when we include the interaction between context and word type. And in terms of interpretation, this means that there are differences in the overall magnitude between levels. So this is the intercept. But since the polynomials are orthogonalized, these are not differences actually in the intercept, but rather in the overall mean of the whole curve. So this tells us that there are differences in the overall mean between the levels of the context, and that this difference in the overall mean is different depending on the word type. So there's a significant interaction. We are not talking about the shape yet. This is just the overall mean. What happens when we check the interactions? So this interaction, for example, that is significant, is telling us that there are differences between the levels of the context, between match and a match, in the steepness of the slope. There are differences in the value of the slope between levels, because we are talking about this linear polynomial. And then this is marginal, but I wanted to show you just to talk about the quadratic polynomial. What we see here is that there are differences in the sharpness of the curve between the levels of the word type. We are going to visualize this, so it will be a little bit more clear in a minute. So this is a way to have the significance of each of the terms, but we don't have any estimates here. We don't know which is the direction of the change. So what we can do is to see the estimates from the summary of the model. So if we get the summary of the model, we will see something like this. And this is like a shorter version of what R gives you. But basically, we will have the estimates. And the p-values, we are not strictly using these p-values. We are using these p-values, but it's a good way to see which one is significant and which is not. So what does this mean? Again, we have the intercept term, the poly 1, poly 2, poly 3. And since these are dummy coded, remember that we have reference levels. In this case, the reference levels are the unmatched context condition and the non-ambiguous word type. So that means that these up to here are the effects of the polynomials in the unmatched and non-ambiguous condition. So, when we start looking at the effects of the variables, what we see is first we have the intercept effects, because we are not including any polynomials yet. These are just the intercept effects. And what we see is that the matched condition reduces pupil size. Why do we know that? Because this estimate is negative, right? So that means that the overall mean for the matched condition is smaller than the overall mean of the unmatched condition, that is the reference level. Then we also see that this reduction is even higher for ambiguous words. And how do we know that? Because when we see the interaction, when this word is matched but is also ambiguous, we have a negative estimate that sums to this estimate over here. So when this word is not only matched, but is also ambiguous, we have an even smaller mean in the pupil size. Okay, so let's go now to the slope effects. If we want to check the slope, we have to check the linear term, that is the poly 1. And what we see is a significant effect of a significant interaction between poly 1 and the context match. That means that the match condition presents a more positive slope than the unmatched condition. So we know that it's more positive because this estimate is positive. But this truly means that this is a less steep fall. Why? Because originally this slope was negative. So what is happening is that this negative slope in the match condition is a little bit less negative, right? But it will be still negative. And then, well, this is the slope effect for the other factor, the ambiguity, the word type, but it's not significant. And finally, we have this marginal effect of the quadratic term, that is that the ambiguous words marginally present a less curvy negative inflection. So we see from this line that the inflection was negative, that is, it is a sad face. And for the ambiguous word, this sad face is a little bit less sad. But this is not significant, but I'm just telling you this to talk about the inflections too. And finally, we have the cubic term that in this case has no interactions with experimental variables. So in the case of the cubic term, this shape will be the same for the match and the unmatched context, and for the ambiguous and the non-ambiguous words. Are we okay?
Yeah.
Okay. Okay, so let's try to see if we can understand this in another way, that is visualizing these differences. What I have here on my right are each of the terms of the polynomial, but separately. So these all summed will make a total function that ideally would be the shape of my, okay, I'm not going, ideally would be the total shape of my pupil response. But if I put them separately, it's easier for us to see these effects that we've been talking about. So what we see here is the overall average. This is the intercept, that remember that as these are orthogonal polynomials, the intercept is talking about the overall average of the whole curve. And remember that we found that the match condition reduces pupil size. This is what we see here, that the match condition presents smaller average than the unmatched condition, that is in red. And we also found a significant interaction between the context, remember here, the context and the word type. So what that means is that this reduction in the mean is higher for the ambiguous compared to the non-ambiguous words, right? So this is the first effects that we saw. And then we also found significant effects in terms of the slope. We saw that the match condition presented a more positive, or what I told you, less steep fall than the unmatched condition. And this is what we see here. You see that the slopes are both negative, but the match condition presents a less negative or a more positive slope than the unmatched condition. And finally, we have the poly 2 and poly 3 terms that, remember that we didn't find any significant interactions between the conditions. So that is why we see exactly the same curves for both of the conditions, right? Another way to play with this is with this Shiny app, in which I will upload the code of this if you want to, so if you want to play and change it. But basically, by default, it starts with the coefficients of my model. So that's why what you see in the total function is very similar to the response that I had for the pupil size, something like that. But you can see what are the effects of changing each of the terms. So for example, well, if the intercept is higher, of course, it will only shift the curve vertically. You won't see any changes in the shape. But for example, if we change the slope for it to be a little bit more positive, that is the case of the match condition, we can see how that changes the shape of the total function. If we put a very negative slope, this will be like, I don't know. It's difficult to explain how it changes the total function, so it's easier to just see it. We can do the same for the quadratic term. Remember that this is negative, so it is a sad phase, but it can also be a happy phase, and the shape of the total function will be completely different. Then the cubic term talks about the sharpness of these peaks. So higher values will result in more sharp curves, and the negative and the positive changes the direction of this. Finally, the quartic completely exceeds my understanding of how it impacts the total function, but it's also in terms of the sharpness of these curves. But I will upload the code of this, so if you ever run a model, you can change these intervals and values to yours, and you can see exactly what happens with your own model. Okay, so going back to the experiment, I'm almost finishing. I just wanted to show you how this can be reported, more or less. So, and just to summarize the results that I've seen. So what we saw is that including the context on the intercept and on the linear term improved model fit. This is what we saw on the table, comparing with the likelihood radio test, comparing the model that included the term with the model that did not include the term. And if we go to the dummy coded variables that we can see in the summary, we can see that the direction of that change, that is what I put here, that is that the match context presented a lower mean pupil size. Here I have the estimate, and a less steep slope. I also have the estimate compared to the unmatched context. And importantly, we also found that the interaction between context and word type also significantly improved the model fit, indicating that the effect of context was larger for ambiguous words compared to non-ambiguous words. And here I also have the estimate. So this is more or less how you would report the results, combining the information that you have on the table with the information you have from the summary of the model. Okay, so I think I'm done. Yes, that's all. Thank you. This is a piece of art that I did for the presentation. They are pupils and curves.
Thank you so much for that tutorial. That was an amazing walkthrough. You covered everything. Does anyone in the room or online have any questions for Julieta?
It's not Julieta, but she want the camera on.
Yeah, can you turn the camera on?
It's locked.
Yeah, go for it. I should have done it.
Hi, Julieta. I don't know if you can see me or hear
Hi.
me.
Yes, I can see you. And hear you.
Okay, so I'm not sure if I understood very well. At some point, you were saying that when you decided, so you created your polynomials with a function and you call them orthogonal polynomials because this way they're not correlated with each other. Yes. But then, or maybe I'm getting confused with the other thing that you showed us before. At some point, I remember that when Drew was presenting a model in the session before, she was saying, in order to not correlate my polynomials, I have to put a -1. No, am I getting super confused with something else? When you were showing a model, and here in the random effects.
So that was a random effects issue where it is different than the creation of the polynomials.
Okay.
So that was a specific thing where I couldn't converge my model, and rather than deleting my random slopes, I did the -1 plus poly, and that's just when you do random slopes within a model and you have multiple nested together, it automatically looks for correlations among them.
Okay.
And you can remove those random effect correlations, but it's
different from when you create your polynomials and you create
Yes.
them orthogonal so that they're not correlated.
Yes.
But then when you insert them as random effects, they can still come up as correlated
This is a good question because the thing is orthogonalized polynomials still have a little bit of correlation. So
Okay.
they're improved, but they aren't perfect.
Okay. Okay, just to clarify that because I was confused about why, like whether there are different ways to create polynomials or not. And okay, thank you.
Anyone else have a question? Are there any questions online? Check the chat quick. Okay. Well, if you think of any questions, you can certainly email me, or I'm sure Julieta as well. Let's thank her again for leading this